Greetings, everyone. Today we're going to talk about thermochemistry, and there's a few definitions that we need to go over first before we can start talking about some more concepts. The first one being energy that transfers from one object to another because of a difference in temperature. Well, it's the title of this chapter, which is called heat. Okay, thermochemistry. Thermo means heat of chemistry. Now, sometimes you're going to see the unit for heat represented in with the letter Q, and sometimes you're going to see it represented with the letter H for enthalpy. So we'll get into that a little bit more detail. Just keep in mind Q and H is going to be represented by heat. All right, next one. Something that's proportional to the average kinetic energy. Well, this should be a review one. This one is temperature. Remember, temperature is the average of all the kinetic energy of the molecules, okay? So hopefully in this unit, you will understand that heat and temperature, not the same thing, not the same thing. So heat is a form of energy, and temperature is an average of all the moving particles, okay? All right, let's do a couple more. Energy is neither created nor destroyed, only moves around or changes to another form. This is one of those laws, okay? So it is the law of conservation Now, before stoichiometry, we did the law of conservation of matter. And since we're doing since we're learning a chapter on heat energy, it's going to be the law of conservation of energy. All right, next one. Object or area in which you are focusing on. Let me change my pen. Something a little less hot. Object in which we're going to focus on. So when we're talking about heat flow, we need to know where the heat is coming from, or where the heat is going. So we have to designate what we're studying. And what we're studying is what's called the system. A little bit darker. So we're going to call this the system. And then anything on the outside of whatever we're focusing on, and that's going to be called the surrounding. Okay, perfect. One thing to note is that I can't measure the system directly with the thermometer. So what we're going to be focusing on mostly is measuring the surroundings. So you're going to have to kind of flip your brain for a second because of the fact that whatever we're using, our thermometer, can't get inside of these chemical bonds or inside of the system. We can only measure things on the outside of the surrounding, and it'll make sense, hopefully, in shortly. All right, so when we talk about heat flow, remember, we can only measure things in the surroundings. And everything, all the chemical reactions, that's the system. So I'm going to write here, if we're going to talk about an ice cube, remember the ice cube and all the chemical bonds, that would be the system. And then everything else is called the surroundings, okay? Same thing, if we had a fire going, the chemical bonds that are breaking and forming in that combustion reaction, that would be the system. So I'm going to write SY, I'll just write both things. System, okay? And that's going to bug me. System. I can't mess up my M for Murphy. All right. Again, everything on the outside of the system is called the surrounding. we can only measure, I can't, like if I have a thermometer, I can't put my thermometer inside little chemical bonds. So my thermometer, let's just pretend my finger, I got a meat thermometer as my finger. If I put my finger on the outside of this ice cube, it's gonna feel cold, except there is no such thing as cold, only the absence of heat. So, just like in the gas chapter, you can't say the word suction because there is no such thing as suction, just high pressure or low pressure. Everybody's pressing. In this chapter, there is no such thing as cold. That is just the sensation you're feeling when there's an absence of heat or low heat. Okay, so we're gonna use my finger as the thermometer. You stick your finger on the outside of the ice cube. It feels less hot. Can't say the C word. Okay, that's because the heat is coming from my finger and going into the system. Whenever heat is going in to the system, we call that endothermic. That's going to be endothermic. When heat is exiting the system, when you stick your finger or a thermometer on the outside of the system, which is the fire, okay, remember this is the outside, the system, you're going to feel a sensation of hot because the heat is exiting. So when the heat exits, okay, we're going to call that exothermic for exiting. Okay, remember everything on the outside of this little system is called the surroundings. Okay, and remember heat is leaving the system and burning that finger. In the ice cube, heat is getting pulled in, pulled in, pulled in. All right, well, that makes pretty good sense. Let's make it a little bit harder. Now, this is not like a I have a hot pack and a cold pack. This is not a hot pack you put in the microwave, and this is not a cold pack you put in the freezer. These are room temperature, and they've got some chemicals. They have some salts in which you break apart, and it mixes with the water that's currently in the pack. So like a lot of trainers have these because they're stored at room temperature. You don't add or remove anything. It's just the chemical bonds dissolving in water. So that being said, hot pack, exo or endo? Well, remember, if this is the system, if these are the system, here's my system, and here's my system. If it's a hot pack, is the heat leaving the hot pack or going into the hot pack? And remember, my hand sits on the outside. We live in the surroundings. There's 5 fingers. So if it feels hot to my hand because I'm on the surrounding, everything outside the system is called the surrounding. That's because heat is going out. And if heat is leaving the system, we call that it's exiting. So it's going to be exothermic, exo heat. Now, what about cold pack? If my hand is on the surrounding, okay, and if my hand is on the surrounding, 4, 5, and my hand feels less hot, that's because heat is traveling from my hand and into the hot pack. Okay. All right, so then if it's going to go in the system, if heat is traveling in the system, then we call it endothermic. Okay, all right, moving on. So we could represent exothermic and endothermic with these energy diagrams. Okay, so they look very similar, but they are mirrored or flip-flop, because that's essentially what exo and endo are. It's just the direction of heat. Either it's going out or going in. Now, this on the y-axis is the potential energy of the system. Okay, so not the surroundings. So this is the potential energy of the system. Now we have reactants, which is sometimes I just put R or a P for products. And they got this big hump for A. And then what you see is this delta H. Now the delta, the triangle just means the change, like the final minus the initial. So what's the gap? All right. Now, in order for a reaction to occur, you need to have a little bit extra energy in order to do so. Okay. Think of this as nature's speed bump, and so that in order to get from point A to point B, from reactants to products, it's not going to make it easy, because this delta H is not a big gap. Okay, so you need to put a little bit extra energy in order to do so. So that being said, this is called my activation energy, often represented with capital E with a lowercase a. Okay, capital E with a lowercase a. That's my energy of activation. It needs a little bit extra energy to get from point A to point B, reactants to products. All right, so if I start with somewhat low potential energy, and at the end I've gained potential energy, so the heat, the system has gained heat. So let's go back. The system has gained heat. If it's gained heat, then it's going to be endothermic. Okay, so it's gained potential energy. It's gained potential energy in the form of heat. Okay, so we're going to say this is called endothermic. Conversely, if I start with reactants and I end with products, and I have gone down in potential energy, I've lost potential energy. Okay, I've gone down versus up. Color that in, make it look nice. Okay. Conversely, if I've decreased in potential energy, that's because my energy left the system in terms of this heat, in terms of exothermic. So exothermic is when heat leaves the system no longer has all that stored potential energy, and we're going to call that exothermic. All right, so look at this hump right now. Not that much for exothermic. So my energy of activation is right here. Energy of activation is a lot smaller typically for exothermic reactions versus endothermic reactions. That's why you see more reactions that release heat than reactions that absorb heat, because typically the endothermic reactions have a higher activation energy in order to get over that speed bump. Okay. All right. So let's do a couple problems. Oh, one thing. Endothermic, since my change in heat at the end of the story, my products went up, it increased, therefore I represent delta H with a positive number. Conversely, for exothermic, my potential energy decreased, and we're going to use a negative in front of that number. So please keep in mind that if you see a number with a positive or negative, that just means the direction of heat flow, not how big or significant the number is. So if it's a negative number, that doesn't mean like I have less heat. No, that just means the heat left. All right, so here we go. So now we have numbers associated with this. So what could A be? Well, A is, let me change my color to something less, it stands out. Remember, this little platform right here is my starting platform, and here's my ending platform. So I have A, we have this big hump. A is where the reactants, and then the top is where my activation energy is. So what A is representing is this gap. So what could A be? A would be the activation energy, or sometimes it's represented with a E sub A for energy of activation. Okay, I'm not going to write that. Now look at B. B is the change in heat because it's reactants minus products. So B is the delta H. What is delta H then? Well, it's products minus reactants. So my delta H is, let's look at products. Products is at 80 kilojoules. I'm going to put kg. Oops, that's 80. And then 160, 80 minus 160 is negative 80 kilojoules. Okay, so again, just because it's a negative number does not mean that it's a small number, it just means the direction. Okay, oh, wait a second, that's negative. So this is an exothermic reaction because my delta H has lost heat. Okay, I've lost heat. I started with a lot and I went down. So I have a negative delta H. Let's do D, and then D would be the just your ending heat. Okay, so your products. And then for determine the, yeah, so we're good with A, B, and then don't worry about C, and then we're good. Let's do the next one. All right, next one looks very similar, a little too similar if you ask me. Okay, sorry, I had to fix that diagram because it was the exact same. So we flipped it now. All right, so if I have reactants, if this is the energy, my heat energy of my reactants, and this is the heat energy of my products, you should be able to look at this diagram and determine if it's exo or endo, the enthalpy of the products, enthalpy of the reactants, and see if it's the heat is is positive or negative. So remember, enthalpy and heat and H, those are all the same thing. All right, so I started, if my reactants were at 80 and my products were at 160, what is my delta H? My C, so C equals, on the diagram, my change in heat. Remember, change in heat is final minus initial. So my change in heat, my final was 160 and my initial was 80. So I ended with a positive 80 kilojoules. Now it's really important that you don't forget those positive and negatives. And the fact that I gained heat, let's go back. I've gained heat. If I gain heat into the system, that means it's going to be endothermic. Okay, so this is going to be an example of an endothermic reaction. The products have more heat energy at the end of the story than they do at the beginning of the story. Now, if you look at letter A, now this is the reactants, and you're going to go up this big hill. Okay, right here for A, you got to go up that big hill. Think of that big hill as like the big speed bump, and we're going to call that the A is the activation energy. Activation energy. And what do we get to? So our activation energy, or our E sub A, is its high is 240, so it's 240 high, and then it starts at 80. Remember, it's not going all the way down. It's not going all the way down to 0. It starts at 80 kilojoules. So 240 minus 80 equals positive 160. All right, so keep in mind that you need to know your reactants, the products, your delta H, whether it's positive or negative, and then the activation energy.